Every year, the world manufactures more than 400 million tons of plastic, and of all the plastic ever made, roughly 9% has been recycled. 9%. The rest sits in landfill, goes up a chimney, or breaks apart into fragments too small to see. In 2024, surgeons in Italy scraped fatty plaque out of the neck arteries of 257 patients and sent it to a laboratory. In 58% of those patients, the lab found polyethylene, shopping bag material lodged in the artery wall. A substance that conquered the planet in a single century is now showing up inside the people who built their world around it. Then, in October 2025, a forestry university in Harbin published a paper in Nature Communications that made materials engineers put their coffee down. China's bamboo plastic is not bamboo powder stirred into resin. It is not a partial biocontent blend. It is built from nothing except the molecules already sitting inside a bamboo stalk. And in testing, it pulled harder than ABS, held its shape at 180 degrees Celsius, while 4 standard commercial plastics sagged and deformed beside it, and then vanished completely into ordinary garden soil in 50 days. If you enjoy videos that take a genuine engineering breakthrough apart and check whether the claims survive contact with the data, hit the like button and subscribe. These take a long time to put together, and it genuinely helps. Now, let us get into it, because the chemistry here is more interesting than the headline, and the limitations are more interesting than either. Start with the question nobody asks properly: why has plastic never been replaced? The lazy answer is that oil companies are powerful and governments are slow. That is not wrong, but it is not the reason. The reason is that plastic solves 4 problems at once, and every replacement so far has only solved 3. Think of it as a triangle with a 4th corner nailed on. A material has to be strong enough to do a real job. It has to break down at the end of its life. It has to cost roughly what plastic costs. And it has to run on machines that already exist in factories that already exist. Hit 3 of those, and you have a laboratory curiosity. Hit all 4, and you have an industry. Look at what happened to the best attempts. Polylactic acid, PLA, is the most successful bioplastic on the market and holds about 31% of global bioplastic share. It is made by fermenting plant sugars, usually from corn. It is genuinely compostable, but only inside an industrial facility running above about 55 degrees Celsius. Toss it in a garden compost heap and very little happens. There is a beautiful and slightly cruel irony buried in this. The 58-degree composting temperature that PLA needs also drives the polymer to crystallize, and higher crystallinity slows degradation down. The condition that is supposed to destroy it partly protects it. In seawater, it is worse. One study ran PLA in a marine environment for 428 days and measured essentially 0 degradation. PLA also softens somewhere around 55 to 60 degrees, which is why a PLA cup and a hot drink are a bad combination, and it is brittle, and it eats farmland. Polyhydroxyalkanoate, PHA, degrades far more willingly, including in seawater, but it is grown by bacteria in fermentation tanks, and fermentation is expensive at every scale anyone has tried. It has been stuck in niche, high-margin applications for years. Starch-based plastics dissolve when they get wet, which rules out roughly everything that might encounter rain. Cellulose acetate performs well but needs aggressive chemistry to produce, which undercuts the entire point. Here is the number that puts all of this in perspective. Global bioplastic production was around 2.18 million tons in 2023. Global plastic production is north of 400 million tons. Bioplastics are not competing with plastic. They are a rounding error on plastic. And on current trajectory, the OECD projects global plastics consumption reaching about 1.23 billion tons by 2060. The cost picture is stranger than most people assume. A kilogram of plastic looks cheap on the invoice. WWF and Dalberg tried to price what that kilogram actually costs across its whole life, counting greenhouse emissions, health effects, waste management, and the damage from waste that escapes management entirely. They landed at roughly 19 US dollars per kilogram in high-income countries and around $150 per kilogram in low-income ones. That is $19,000 a ton against a market price of somewhere near $1,300. Nobody pays that bill directly. Everybody pays it eventually. So the wall was never really environmental. It was a materials science problem, and it sat at the molecular level. Which brings us to what the team in Harbin actually did, and it is worth being precise, because most of the coverage has been sloppy about it. Bamboo is mostly cellulose. Cellulose is the most abundant structural polymer on Earth, and it is already, chemically speaking, a long-chain molecule. The chains are strong. That is not the problem. The problem is what holds the chains to each other. They are locked together by hydrogen bonds, an enormous dense network of them, arranged in a rigid crystalline pattern. Picture millions of microscopic magnets clamping every chain to its neighbors in fixed positions. That network is why a bamboo culm can stand 20 meters tall and flex in a typhoon without snapping. It is also exactly why you cannot make plastic out of it. Real plastic is thermoplastic. Heat it, it flows, you pour it into a mold, it sets. Cellulose will not do that. Heat it far enough and it does not melt, it chars. Try to force bamboo into a new shape and it splits along the grain. The material is strong precisely because it refuses to be reorganized. Every previous bamboo plastic dodged this rather than solving it. Grind bamboo into fiber, mix the fiber into a petroleum resin, and mold the composite. You get something reasonably strong with a nice sustainability story on the label, but the resin is still oil, the resin is still what holds it together, and the resin still does not biodegrade. You have made bamboo-reinforced plastic, not bamboo plastic. The Harbin approach, led by Haiping Yu and Dawei Zhao, with first author Hongying Tong, was to take the hydrogen bond network apart and then rebuild it, denser and tighter than nature had it. Think of unraveling a knitted jumper down to loose yarn and then knitting it back up at half the stitch spacing. Same yarn, different fabric, considerably stronger fabric. It is usually described as a two-step process. It is really four, and the steps that get skipped matter. First, the bamboo has to be turned into clean cellulose. Bamboo chips are delignified using a peroxyformic acid solution at 50 degrees for 12 hours, then neutralized with dilute sodium hydroxide and washed. Lignin, the glue that stiffens plant cell walls, comes out. This is a chemical pulping step, and we will come back to it. Second, the cellulose goes into the solvent that does the real work. It is a deep eutectic solvent, zinc chloride and formic acid, and water mixed at a molar ratio of 1:2:2. Stir for 90 minutes at room temperature and the crystalline hydrogen bond network comes apart. The chains separate into a thick, uniform, pourable molecular solution. Crucially, the chains themselves survive. The degree of polymerization, the average chain length, stays around 730. And along the way, something useful happens. Some of the hydroxyl groups on the cellulose react with the formic acid and become formate ester groups at a substitution level of about 0.4. Remember those, they become the anchor points later. Third, and this is the step almost every article omits, the solution is spread out and soaked in a 48% calcium chloride bath for 2 hours. The calcium ions trigger the chains to reform bonds with each other and with water, and the whole thing sets into a soft, flexible hydrogel. It is 83% water, and it pulls at about 9.65 megapascals, respectable for a gel, nowhere near a plastic. Fourth, the gel is washed and then immersed in pure ethanol for 12 hours. The ethanol strips out the water that has been propping the chains apart. With the water gone, the chains collapse together, and the new hydrogen bonds that form are between the hydroxyl groups and those formate ester groups from step 2. They pack tighter and more orderly than the original bamboo. X-ray diffraction shows the structure convert from a broad, disordered signature into sharp, crystalline peaks, characteristic of a different crystal form entirely. Electron microscopy shows the pores disappear, 12 hours of air drying, and you have solid material. The jump is dramatic. Tensile strength goes from 9.65 megapascals in the gel to 110 megapascals in the finished plastic. Young's modulus goes from 1.7 megapascals to 2.2 gigapascals. That is an increase of more than 1,200-fold in stiffness. Nothing was added. No filler, no resin, no reinforcement. The same molecules rearranged. So, how good is the result, really? Here the evidence is better than you might expect, because the team ran head-to-head comparisons rather than citing data sheets. The most striking test is thermal. They put samples of BM plastic alongside ABS, high-impact polystyrene, nylon 66, and acrylic into a 180-degree environment for 2 hours. The 4 commercial plastics deformed and turned brittle. The bamboo plastic held its shape and could still be bent without breaking. Dynamic mechanical analysis puts its glass transition above 150 degrees, and even at that temperature, it retains a modulus around 3.6 gigapascals. Its coefficient of thermal expansion is about 40.7 parts per million per Kelvin, which means it moves very little as temperatures swing. 7 days at 100 degrees and 7 days at minus 30 degrees produced no meaningful dimensional change either way. On mechanicals, it reached 110 megapascals in tension, or 103.77 in the direct comparison against the commercial set, with a flexural strength of 97 megapascals and a flexural modulus of 6.41 gigapascals. That flexural modulus is the number engineers should look at hardest, because stiffness and bending is what determines whether a panel sags. Impact strength came in at 110 kilojoules per square meter. It is also close to optically clear at thin gauge, with about 90% light transmittance at 0.15 millimeters. The degradation test was deliberately unglamorous. Samples 40 millimeters by 20 by 1, buried 6 centimeters deep in natural soil at 25 degrees. No inoculation, no heated vessel, no controlled humidity. Just dirt and whatever microbes live in it. Within 50 days, the bamboo plastic had fully disintegrated. In the same soil, ABS, HIPS, nylon 66, and acrylic showed negligible change. PLA and PBAT, the 2 mainstream compostable plastics, only partially degraded. Recycling worked too, and worked chemically rather than mechanically. Waste fragments were dissolved back into recovered solvent, regelled, re-stimulated with ethanol, and reformed. The recycled material came out at 97 megapascals and 2.7 gigapascals, about 90% of the original strength retained, which is genuinely unusual. Conventional mechanical recycling shortens polymer chains every pass, which is why recycled plastic ends up as park benches rather than going back into the product it came from. They also showed it is not confined to test coupons. Injection into molds produced gears and small components. Casting and molding produced lampshades and containers. A sheet 50 centimeters by 35 was mechanically formed into honeycomb and corrugated panels, which are structural shapes, not decorative ones. Now the part that gets left out of almost every article about this material, and the part that actually determines whether it matters. Water. That 110 megapascal figure is a dry number. Expose the material to 90% relative humidity for 48 hours, and tensile strength falls to 43.24 megapascals. Immerse it in water for 24 hours, and it falls to 22.85 megapascals, from 110 down to under 23. That is not a footnote. That is roughly 80% of the strength gone after 1 day in water. And here is the uncomfortable part. That sensitivity is not a manufacturing defect that better processing will fix. It is the same property that makes the material biodegrade in 50 days. The structure is held together by hydrogen bonds, and water competes for hydrogen bonds. The mechanism that lets soil microbes take it apart is the mechanism that softens it in the rain. Every strong, cheap, genuinely biodegradable material runs into some version of this trade-off, and this one is no exception. The researchers are upfront that the material retains attractive properties after wetting, which is fair. 23 megapascals is not nothing, but anyone imagining outdoor structural bamboo plastic should adjust expectations sharply. Second constraint, it is rigid. Strain at failure is under 5%. That is fine for a gear, a housing, a panel, a handle. It is useless for film. no bags, no cling wrap, no flexible pouches, and flexible packaging is a very large share of the plastic problem, particularly the share that leaks into the environment. This material does not address that segment at all. Third, throughput. The ethanol stimulation takes 12 hours. The drying takes another 12. That is roughly a 24-hour cycle to produce one part. An injection molding machine running polypropylene produces a part in tens of seconds. Yes, the process runs at room temperature and skips the enormous energy cost of melting, which is a real advantage. But a factory does not run on energy cost alone. It runs on parts per hour, and a 24-hour cycle is not competitive with anything unless you can parallelize it massively. That is a solvable engineering problem in principle. It has not been solved yet. Fourth, the chemistry is cleaner than the alternatives, but it is not clean in absolute terms, and the coverage has been generous here. Zinc chloride is classified as corrosive, harmful if swallowed, and very toxic to aquatic life with long-lasting effects. Formic acid is corrosive. The delignification step uses hydrogen peroxide, formic acid, sulfuric acid, and sodium hydroxide. Recovering the solvent for reuse requires adding sulfuric acid to precipitate out the calcium. None of this is exotic or unmanageable, and all of it is standard industrial practice, but no toxic byproducts, is a claim relative to conventional cellulose processing, not an absolute one. And at industrial volumes, zinc-bearing effluent is a real permitting question, not a rhetorical one. Fifth, closed-loop recycling has a limit. The chain length drops from around 730 in the original material to around 424 in the recycled batch. Strength held at 90% through one loop. Nobody has published what happens after 5 loops or 10. The chains are getting shorter each time, and eventually that has to show up in the mechanicals. Sixth, cost. The techno-economic analysis puts production at $2,302 a ton. The framing matters enormously here. Against nylon 66, acrylic, and high-impact polystyrene, the engineering plastics it actually competes with on performance. That is competitive, and the paper's own comparison places it between those and PLA. Against commodity polypropylene and polyethylene, which traded somewhere in the region of $1,200 to $1,600 a ton through mid-2026, it is roughly 1.5 to 2 times the price. So the honest version is this. As a replacement for engineering plastics, the economics already work. As a replacement for the cheap commodity resin in a yogurt pot, they do not yet. Feedstock is 38% of the cost. Solvent and ethanol recovery another 24%, and electricity only 3.3%, which tells you the room temperature process really is doing its job. And seventh, the honest structural caveat. As of now, this is a laboratory result with a very good pilot demonstration behind it. There is no announced commercial plant, no published pilot line output, no independent replication I can find. The largest object demonstrated is a 50 by 35 centimeter sheet. That is not a criticism of the work. It is where the work is. So why does any of this deserve more attention than the dozens of promising bioplastics that came before it and went nowhere? Because of what sits behind it. Most breakthrough materials die on feedstock. You invent something wonderful that requires a plant which grows in 3 valleys, and it never scales. Bamboo has the opposite problem. There is too much of it to ignore. Bamboo yields up to 78.3 tons per hectare, about 4.5 times what conventional timber produces on the same land. Some species add over 1 meter of height in a day. Cut it, and it regrows from the existing rhizome system. No replanting, no reseeding, no land clearing, with a harvest cycle of 3 to 5 years against 25 to 30 for a pine plantation. Corn has to be sown from scratch every single season, and it competes directly with food. Bamboo grows on slopes and degraded ground that arable farming has already given up on. And it is a grass, not a tree, which is why the growth rates sound implausible until you remember what grass does to a lawn in a week. China has close to 8 million hectares of it, over 500 species, and annual bamboo output of roughly 150 million tons. The processing industry around it is not a plan. It is already operating. More than 10,000 enterprises, over 15,000 distinct product types, and an annual output value that the National Forestry and Grassland Administration reported in January 2026 as exceeding 520 billion yen, around 75 billion US dollars. In 2010, that figure was 82 billion yen. That growth is policy-driven, and the policy is explicit. In November 2021, a group of ministries issued guidance on accelerating bamboo industry development. In October 2023, the National Development and Reform Commission, the Ministry of Industry and Information Technology, the Ministry of Finance, and the Forestry Administration jointly published a 3-year action plan specifically for substituting bamboo for plastic, with 6 objectives and 23 defined actions. A month later, China and the International Bamboo and Rattan Organization launched a global action plan on bamboo as a substitute for plastic running to 2030, and it is producing hardware, not white papers. Bamboo wound composite pipe, a Chinese-originated infrastructure material, has now been installed across more than 700 kilometers in 11 provinces in municipal, water, and transport projects, reportedly raising production efficiency by 25% and cutting unit cost by 13%, replacing steel and cement in applications where nobody expected a grass to show up. In early 2026, a tilt-rotor fixed-wing drone flew at Tianjin with more than a quarter of its structure, including the entire fuselage skin made from bamboo composite. 2.5-meter wingspan, 7 kilograms, over 100 kilometers an hour, more than an hour of endurance. The bamboo sheet costs about a quarter of what carbon fiber cloth costs, and the aircraft came out over 20% lighter than a comparable carbon fiber build. In Anji County in Zhejiang, 66,000 hectares of bamboo support around 1,000 companies producing over 20 billion yen of output, shipping to roughly 110 countries. That is the strategic point, and it is worth sitting with. The bamboo plastic paper does not exist in isolation. It arrives on top of an industrial base, a supply chain, a policy framework, and an export network that were built over 15 years for a different reason and happen to be exactly what a new bamboo material needs. Now, compare that to what the international system has managed. Negotiations for a global plastics treaty were supposed to conclude by the end of 2024. Busan failed. A resumed session in Geneva in August 2025 failed. The chair resigned that October. In February 2026, the committee reconvened in Geneva for a single day, purely to elect a replacement, Ambassador Julio Cordano of Chile, with no treaty text on the table at all. Substantive negotiations are expected to resume later in 2026, more than 18 months past the original deadline. Set those two timelines side by side, and the lesson is uncomfortable but clear. One approach is trying to negotiate plastic down through 175 governments. The other is building the replacement industry and letting it compete. Whatever the treaty eventually says, the countries and companies that already have the factories, the feedstock, and the material science will be the ones selling into whatever market it creates. The rest of the world is not locked out of this either. FAO puts global bamboo cover at around 35 million hectares, and INBAR thinks the real figure could be closer to 50 million once underreporting is corrected. Roughly 71% is in Asia, 16% in the Americas, 13% in Africa. The plant is not a Chinese monopoly. The processing industry currently more or less is. So where does that leave the claim in the title? Not with a plastic replacement, with something more specific and more useful. Somebody has demonstrated with published data and a peer-reviewed method that you can take the most abundant structural polymer on Earth, disassemble its bonding network at room temperature, rebuild it denser than nature made it, and end up with a material that beats engineering plastics on stiffness and heat and then goes back into soil in under 2 months. That trade-off was supposed to be impossible. It is not impossible. It is just difficult. And now somebody has the recipe. What it cannot do yet is survive a rainstorm at full strength, stretch into a film, come off a line in seconds rather than a day, or match the price of the cheapest resin in the world. Those four things are the whole distance between an excellent paper and a material in your car door. Some of them are engineering problems that scale and money will solve. The water one may be closer to physics than to engineering, and physics does not negotiate. The world took a century to build its dependence on a material that never goes away. It will not unwind in a decade, but the argument has finally shifted. For a long time, the honest answer to why not replace plastic was because nothing else works well enough. That answer is now, for a real and growing category of parts, no longer true. If this changed how you think about a material you touch 100 times a day without ever wondering what it is made of, drop a like and subscribe. Turn on notifications so the next one finds you. And here is my question for the comments. Given that this material's greatest weakness, its sensitivity to water, is the exact same property that makes it biodegrade, do you think that trade-off can ever really be engineered away? Or is every truly biodegradable structural material going to be stuck making the same compromise? Tell me what you think below. I read them.